Mid-Pacific, late 1943. Night watch aboard a U.S. Navy destroyer, its hull shuddering through heavy swells. Below deck, where no starlight reaches, the engine room breathes like a living animal. Heat presses in from every surface. Oil mist clings to the air. Steel pipes vibrate. Boiler gauges tremble. It is a world measured in pressure, temperature, fuel flow, and endurance. A machinist stands with his sleeves rolled high, hands darkened with grease and powdered metal. He has worked this engine for months, listened to it, felt it, understood its habits better than any manual ever printed. He knows how much fuel the ship burns every hour of patrol, every minute of full speed, every second of combat alert readiness. He also knows that they are burning too much tonight. The destroyer is days from resupply. Carrier operations continue ahead. Japanese submarines hunt the refueling ships behind. The machinist looks again at the fuel valve assembly, a design he has been quietly studying, sketching, reconsidering. A thought he has repeated for weeks solidifies now. Something here can be changed, and this is where the story begins. By late 1943, the Pacific War had entered a new phase. The United States was no longer reacting. It was advancing. Island by island, airstrip by airstrip, the Navy pushed west across the Pacific. But every mile gained came with a cost measured not only in lives but in fuel. The distances were enormous. Destroyers, fast, versatile, essential warships, were constantly in motion. They screened aircraft carriers, hunted submarines, escorted supply convoys, and bombarded enemy shore positions. Their engines rarely cooled. Their bunkers rarely stayed full. A single destroyer could consume thousands of gallons of fuel oil in a day at combat speed. Fleet planners knew this, but the Pacific did not care about planning. The ocean was vast, refueling ships were limited, and Japanese submarines lurked like wolves beneath the waves. Every destroyer that ran dry on patrol became vulnerable. Every destroyer forced to leave station weakened the screen that protected carriers. The very heart of American offensive power. The U.S. Navy had industrial muscle behind it. But logistics in the Pacific were not theoretical. They were immediate, unforgiving, and often desperate. This is where the machinists lived. Below deck, in the heat of the engine room, machinists' mates worked shifts that blurred together. They monitored pressure gauges, tuned feed pumps, adjusted oil sprayers, and listened for the subtle change in engine rhythm that meant trouble. They did not command fleets. They did not write strategy memos, but they ensured the destroyers could move. And movement was life. Among these men were those with a gift for understanding machines not just by instruction, but by intuition. They knew when a boiler was running rich, when a valve was vibrating against tolerance, when fuel wasn't burning cleanly. They noticed the small inefficiencies that, over days and weeks, added up to real loss. The machinist at the center of this story was one of them. He had learned his trade in civilian industry, not a naval academy. He had worked with engines before the war, adjusting them by ear, by smell, by feel. When he entered the Navy, he discovered that military engineering valued standardization and procedure, consistent processes across hundreds of ships. But he also discovered something else. Ships, like people, had personalities. Two destroyers of the same class, built from the same steel, supplied from the same shipyard, could burn fuel differently depending on ocean temperature, crew technique, or subtle variations in valve fitting. Manuals could not predict these things. Only experience could, and he watched. He measured. He kept his own notes. He noticed that when the ship ran at steady cruising speed, fuel efficiency was acceptable. But destroyers in the Pacific rarely cruised. They surged, slowed, maneuvered, patrolled, operating in constant readiness states that wasted fuel. The culprit lay in a specific component, the fuel oil control valve feeding the burners in the boilers. The standard Navy design delivered consistent pressure, but at low or quickly changing demand levels, it overfed fuel, sending unburned oil into the exhaust. That meant lost endurance hours lost, miles lost, operational flexibility lost. The machinist believed that adjusting the valve aperture and flow geometry, a wasteful idea in the eyes of some officers, because it meant diverting time and material away from other maintenance, could reduce that loss. The theory was simple, but implementing it required altering a Navy standard component. Technically, this was discouraged. The Navy prized uniformity. Replacement parts had to fit across the fleet. Modifications complicated logistics. So the proposal went nowhere, until the destroyer was pulled into extended screening operations around the Solomon Islands, where fuel lines were stretched thin, weather-disrupted supply convoys and Japanese submarines prowled the approaches. There were days when the engine room received orders to hold station for hours at readiness, consuming fuel without moving forward. The machinist watched the fuel gauges drop and calculated distances to the nearest tanker in his head. He realized that if the destroyer burned at this rate, it could be forced to withdraw, leaving the carrier group more vulnerable. What he had studied quietly for months suddenly mattered. The ship would need every hour it could get. Every gallon conserved would count, and the engine room was where that battle would be fought. The context of the war had shifted from strategy on maps to survival in machinery. And now, the question was clear. Would the Navy trust the instinct of one machinist and/or the safety of its standardized designs? The tipping point was coming. In early 1944, destroyers of the U.S. Pacific Fleet were operating farther from established fuel depots than ever before. The advance into the Central Pacific, from Tarawa to the Marshalls and toward the Marianas, demanded constant naval presence. Carrier groups needed scouts. Landing forces needed fire support. Transports needed escorting. The destroyer was the backbone of all of it. But every operation came down to the same logistical truth. Fuel tankers had to keep up. If they didn't, destroyers were forced to withdraw. Admiral Raymond Spruance's staff had documented the issue repeatedly. Reports emphasized that destroyer screens sometimes consumed fuel faster than the fleet could sustain. Captains devised rotating refueling schedules, but the distances, weather, and unpredictability of combat made planning unstable. More than once, destroyers nearly fell out of formation because they simply ran low. No one wanted to be the ship left behind in enemy waters. Below deck, those realities were far more personal. Machinists' mates worked in confined, humid spaces where the temperature near the boilers could exceed 120 degrees Fahrenheit. The noise was constant. The metal decks vibrated. Sweat never evaporated. It just mixed with oil and heat. But down there, they also had control. Not over strategy, but over efficiency. Monitoring the fuel oil system required constant vigilance. Fuel was preheated to improve atomization before entering the burners. Steam pressure had to match engine demand to keep the ship's speed steady. A slight misalignment, a clogged sprayer plate, a sticking valve stem, all of it cost fuel. Too much loss and speed dropped. Too little speed, and the ship could not keep its place in formation. The machinist who had studied the control valve system understood that the inefficiency was not dramatic. It was incremental. A fraction of a gallon wasted every minute. But multiply that over a week at sea, and it meant hours of lost operating time. A destroyer running out of fuel was not simply inconvenient. It was dangerous. If forced to stop for refueling at the wrong moment, the ship could become a target. It could expose supply tankers to attack. It could weaken the protective ring around the carriers. In naval warfare, vulnerability invites catastrophe. The machinist had watched this tension build. He had seen the logs. He knew how the ship's endurance fluctuated depending on sea state, speed changes, and operational tempo. He understood that the Navy's standard valve design worked well in controlled conditions, the kind seen in shipyard testing. But the Pacific was not controlled. He proposed altering the valve flow path to ensure steadier fuel delivery at variable loads, especially during extended low-speed or maneuvering operations. This wasn't a revolutionary redesign. It was precise refinement. A small change in how the valve throttled flow could prevent overfeeding. Less unburned fuel meant more propulsion energy for the same amount of oil. But there was another obstacle: hierarchy. A junior machinist did not simply redesign Navy equipment. Changes required approval. Approvals required justification. And justification required proving that the standard system was insufficient, something that could reflect poorly on officers responsible for machinery oversight. In wartime, careers and reputations were guarded just as carefully as ships. Yet the Pacific did not allow complacency. Fuel shortages worsened during sustained operations around the Mariana Islands. Tanker convoys were stretched thin, harassed by Japanese submarines. One missed rendezvous could disrupt an entire battle plan. The destroyer carrying our machinist was ordered into a prolonged screening mission. one expected to last significantly longer than originally scheduled due to delays in carrier airstrikes. Fuel stores were already tight. The engineering officer ordered stricter monitoring and conservation, but the machinist saw that standard procedures would still fall short. Withdraw now and the carrier group would lose part of its defensive ring. Stay on station without enough fuel, and the ship risked immobility. One evening, during reduced readiness cruising at variable throttle, the exact condition where the I valve inefficiency was greatest, the machinist presented his data quietly but directly. Burn records, pressure logs, flow rate estimates, endurance projections. It was not dramatic, not cinematic. It was engineering. The chief engineer listened. He had felt the same anxiety every time the ship refueled at sea while submarines prowled nearby. The log supported the machinist's case. The numbers were clear. Unless the ship changed how it burned fuel, it would have to leave station, and leaving station was not an option. The chief gave permission, not formally, not in writing, but with a sentence spoken in steel heat and engine noise. If it works, we stay out here longer. In that moment, responsibility shifted from manuals to hands, from standardization to ingenuity, from procedure to necessity. The machinist retrieved his tools, and the heart of the destroyer, its boilers and valves, was about to change. The next section will examine how this innovation worked, from the mechanical principle to the human judgment that enabled it. The engine compartments of a World War II destroyer were not glamorous. They were the least seen but most critical spaces on the ship. Battleships and carriers had larger engineering crews. Cruisers had room to spare. But destroyers were compact, every inch optimized. Below deck, space was measured in breadths. Pipes ran overhead. Valves, gauges, and dials turned the walls into a dense field of metal and steam. The machinist and his fellow mates worked in this environment for hours at a time. They learned the ship not by diagrams alone, but by sound, the pitch of the blower fans, the rhythm of the feed pumps, the subtle vibration of boiler tubes when pressure fluctuated. They could tell when efficiency dropped without even reading the gauges. This was not guesswork. It was experience-shaped instinct. The machinist's idea did not emerge overnight. It grew from repeated observations, minor inefficiencies that others accepted as just how the system runs. He had watched how fuel pressure spiked when throttle changes came too quickly. He had monitored how much unburned oil was expelled when burners were adjusted for acceleration. He had counted the minutes of endurance lost to these adjustments. Every drop of oil wasted meant shortening the destroyer's range. And range in open ocean warfare meant survival. The machinist knew that the difference between returning to the fleet and being stranded alone in hostile waters could be measured in gallons. His valve improvement was born not from theory, but from the reality of sweat, heat, and responsibility deep within the hull. The destroyer's endurance would be extended not by orders from admirals, but by hands-on metal in the ship's core. The existing Navy fuel valve was built for standardization. The Bureau of Ships designed equipment that could be installed across dozens of destroyer classes. Reliability mattered more than optimal performance in every condition. A valve that delivered enough fuel under most circumstances was acceptable. But destroyers did not operate under most circumstances. They surged, slowed, maneuvered, and responded to threats faster than larger ships. Their engines lived in constant adjustment. A perfect straight-line cruise at steady speed was rare. The machinist focused on the fact that fuel systems were optimized for the shipyard test bench, not open ocean war maneuvering. The key issue: when throttle demands changed rapidly, the valve tended to overfeed fuel before stabilizing. That brief surge did not translate to propulsion. Combustion wasn't fully efficient at those transitional moments. The result was small, repeated losses, invisible in any single moment but costly over time. The machinist's modification adjusted the flow rate curve. He reshaped how the valve responded to incremental changes in pressure, making the system more precise at partial openings. It did not increase peak power. It did not change maximum speed. What it changed was control, less wasted fuel during transitions, smoother boiler response, more efficient burn. A destroyer rarely needed full combat speed for long, but it always needed to be ready for it. The machinist's redesign preserved readiness without draining endurance. It was not a breakthrough of innovation, but of refinement, and refinement in war can become decisive. In the Pacific War, distance defined strategy. Carrier task forces could strike far, but only if their destroyers could protect them far. The farther operations pushed from support bases, the more every gallon of fuel mattered. A destroyer that could stay at sea 32 hours longer was not simply more efficient, it was strategically transformed. With the machinist's valve improvement, the destroyer could stay on station when others had to peel away for refueling. It could maintain anti-submarine screens during critical windows, when Japanese submarines sought to exploit gaps in formation. It could escort carrier groups through prolonged engagements without weakening the defensive perimeter. A destroyer, out of fuel, was more than a ship in need. It was a vulnerability. But a destroyer with extended endurance became something else. A ship that kept the formation intact. A ship that did not need to break off. A ship that remained where it mattered. In naval warfare, the difference between maintaining formation and losing cohesion could define an entire battle. This machinist, unknown to grand strategy, unknown to military history books, had given the destroyer, and therefore the task force, time. Time to stay at sea. Time to remain combat ready. Time to avoid risk. And time, in war, is often the difference between victory and loss. While U.S. destroyers struggled to stretch range during prolonged patrols, the Imperial Japanese Navy faced a harsher problem altogether. Their fleet oil supply came primarily from the Dutch East Indies, a vast distance across submarine-infested waters. Every transfer, every tanker, every drum of oil was a strategic gamble. Japanese destroyers, especially the famed Kagero and Yugumo classes, were designed for speed and striking power. Their engines were efficient at high output, suited for swift night attacks. But at low cruising speeds, the speed of patrol, waiting, escort, and endurance, they burned fuel at an alarming rate. The Japanese Navy had built ships for decisive engagements, not prolonged war of attrition. By late 1942, Japanese naval commanders were increasingly cautious about sortie distance. They began limiting patrol ranges. They avoided aggressive pursuit when unsure of fuel points. They even abandoned stranded units rather than risk tankers. Fuel was not simply fuel, it was strategy, morale, and reach. So when U.S. destroyers in the Solomons began holding station longer than expected, remaining on patrol days after the Japanese estimated they must withdraw, something shifted. Japanese staff officers miscalculated enemy endurance. Commanders ordered attacks assuming the Americans would soon retreat, but they didn't. And in war, remaining when your enemy expects you to be gone can be the difference between ambush and survival. The machinist's modification was already influencing more than machinery. It was influencing enemy decision-making. Life in the engine spaces of a destroyer was more than mechanical routine. It was a craft, a rhythm, a fraternity. Men worked shoulder to shoulder in temperatures sometimes exceeding 120 degrees and 49 degrees. They slept close, labored close, and trusted each other utterly. And within that world, rank mattered less than competence. The U.S. Navy in World War II, especially aboard destroyers, built a culture where practical knowledge mattered more than strict adherence to manuals. If a man could do something better, and could prove it worked, he was listened to. The destroyer was a ship of problem solvers, men who filed burrs out of valve seats, improvised gaskets from leather, and coaxed another 100 hours from engines designed for half that. This culture mattered. It meant the machinist's observations weren't dismissed as not procedure. They were recorded, tested, discussed, and finally, allowed. His superiors didn't need him to be an engineer from a naval academy. They needed him to be a man who listened to steel and steam with the patience to understand them. This was American naval strength at its quietest. Innovation not written in blueprints, but in grease-smudged notebooks and lived experience. On paper, fuel is a quantity, barrels, gallons, percentage of reserve. In practice, fuel is time. Time to remain on station. Time to escort a convoy. Time to continue pursuit. Time to avoid withdrawal when the enemy expects it. A destroyer that could stay at sea 32 hours longer didn't just save fuel. It gained time. It gained presence in waters where absence meant Japanese supply convoys moved freely under the cover of darkness. That presence influenced everything. Patrol grids widened. Hunter-killer groups stayed out longer. Surprise encounters increased. Japanese destroyers found their assumptions wrong. And in the Solomons, where every night battle was a game of nerves and geometry under starlight, being there when expected to be gone reshaped engagements. This is the heart of the machinist's design. He didn't just change a valve, he changed time, and soon, that extra time would shape a specific confrontation in Iron Bottom Sound, one that would be remembered for decades. The turning point was close. War often highlights grand strategies, massive fleets and decisive battles. Yet sometimes it is the smallest acts of ingenuity that shape the course of history. A single machinist working quietly in a naval workshop altered the endurance of American destroyers with a simple valve modification. What seemed wasteful at first became the linchpin of tactical advantage, enabling sustained operations across the vast Pacific. The human dimension of this innovation cannot be overstated. Sailors on board could operate longer, strike with precision, and remain confident that their ships would carry them through danger. Lives were preserved, missions accomplished, and enemy plans disrupted, all because of a combination of skill, foresight, and technical insight. The machinist's work bridged the mechanical and human elements of warfare, showing that engineering excellence directly fuels tactical and moral superiority. Beyond the immediate battlefield, the adjustment reshaped the Navy's operational doctrine. Extended destroyer endurance reduced dependence on logistics, increased flexibility for carrier task forces, and allowed continuous pressure on Japanese forces. What began as a seemingly minor improvement rippled outward, amplifying industrial capacity, operational tempo, and strategic reach. History often remembers admirals and generals, but the quiet contributions of technical specialists, engineers, machinists, and mechanics form the backbone of victory. Leyte Gulf, one of the Pacific War's most consequential battles, demonstrates this truth. Endurance, ingenuity, and attention to detail became as decisive as firepower, proving that innovation at the smallest level can dictate the outcome of monumental events. In the end, the machinist's wasteful valve was more than a mechanical adjustment. It was a symbol of American resourcefulness, adaptability, and relentless pursuit of advantage. It reminds us that in war, as in life, even the most unassuming contributions can have extraordinary impact. The Pacific theater would continue to test endurance, skill, and courage, but the lesson endured. Small innovations, when executed with foresight and precision, could tilt the balance of history.